is finish up what I was doing last time about showing the parallels and all this stuff. And we're going to get into chapter 8 material and hopefully into windowing today. I didn't talk about windowing before, but now chapter 8, I'm going to tell you a lot of this has to do with programming. And unfortunately, the quizzes and tests don't allow programming, so there may be an assignment or something. There's a couple of assignments related to this. Just want you to know that. I'm going to try to do this in a way that's most valuable to you where you are in your career. I'm not going to try to do anything too abstract and try to make it all applicable to things you're going to encounter the next couple of semesters. Now you're going to learn a lot of stuff about this filtering and stability in your other courses in signals and, in random signals and systems, and in really in controls, and if you take digital signal processing, and I encourage you to do so, radar, digital image processing, and a lot of the other courses that are higher level, you're going to learn a lot about data processing, the way to massage it. Not truly data mining, even though that is one aspect of it, but almost everything will sort of, you'll see the applications. That's what I'm trying to do. Now, last time what I did was, I'm going to put the transforms down and show you the parallels, things you have to see and understand. And I'm not even going to bother with convolution right now. So first thing we did was Laplace, and we had x of s equal to the integral from 0 to infinity of x of t e to the minus st dt. And that was, of course, that's an analysis. Really, it's just the definition of Laplace transform. If we wanted x of t, and we had a Laplace transform, technically it would be this. But we don't do that, do we? We use partial fraction expansions to get the inverse. We do this all the time. Or we use, we know 3 or 4 transform pairs, and then we just use applications. But that's Laplace in a nutshell. And it's very powerful for designing filters, for really finding out, or building systems that will allow filters to be developed. Where we went with that is we used operational amplifiers, capacitors, and resistors to construct filters. That's what we did. Now, the next thing we did was Fourier transforms. And we had x of omega equal to the integral from minus infinity to infinity of x of t times e to the minus j omega t dt. Again, this is analysis. We're analyzing a signal here. And then we synthesize signals. Now, we can do this, but how did we always get the inverse if we wanted it? Do you remember? We did know transform pairs, but there was one powerful technique that I always mentioned. Duality. Don't forget that. You're going to see that again. I mean, you're going to see it several times. And on the final guarantee, you're going to see it. You have to understand duality well in order to really appreciate Fourier transforms. And it's something, the last exam, there were a lot of problems with duality, as I recall. A lot of people didn't understand the direct parallel from it, and I'll spend more time on it. All right, so this is again continuous time, and really these are tools for analysis of a signal, and this is really something with Laplace we can construct filters. All right, we can construct filters that we want basically, and it's fairly straightforward to do that. If you know you want a low pass filter at a certain frequency, you can build it with capacitors and capacitors, resistors, and op amps fairly easily, as long as you know what you want. Now, after that, these are continuous time. Now we're moving into digital signal, the real world, digital processing, where we have finite memory, we have digital signals, we quantized everything. First thing we did was the DTFT, and that was, I better put that down, DTFT, and that was x of omega, and that's the summation from n equals minus infinity to infinity, x of n times e to the minus j n omega right there. Right? And by the same token, we had x of n, and that was the integral from minus pi to pi, right? 1 over 2 pi of x of capital omega times e to the minus, or plus j and omega d omega. Now, this one's important. This is again something where we took this definition and we used a sampled signal here. We literally put in a sampled signal into this equation, turned the crank, and out came this. You'll notice in this one thing that you should note is TS, the sampling interval, is not shown. It's just like when you did, remember when you did your circuit analysis, you had 10 at an angle like 30 degrees, and then you would have an inductor with J 30 ohms and a resistor of 10 ohms. They didn't say the frequency. He just wanted everything in terms of the phasor domain, magnitude of current or voltage. Y'all remember that? The frequency was something that was assumed, known, if needed. In other words, if you wanted the time domain form. So this, again, is the DTFT. This requires an infinite series. Now, there is one important thing to catch here, that this and this can render the same exact bit of information. Do you all remember that, class? And that is, if this transform pairing here, if x of omega has non-zero values only between minus pi and pi, and you know what x of t is, then if you have the same exact formula here for x of capital omega, then you can get x of n by just finding this x of t and replacing it, the t with n. How many remember doing that, right? And we found the one common one was with that, when we had an ideal band pass filter in the frequency domain. We found out, however, that the impulse response to that was what? The sinc function, and that's non-causal. So that's the one thing to keep in mind. That's the DTFT. And we've worked through that pretty well. Then we went to the Z transform. So then we had x of z, and these are all discrete time here. The Z transform was x of z is the summation from n equals 0 to infinity of x of n times z to the minus n, right there. And I'm just going to say one thing. This function right here is virtually identical to this function if you allow z to be equal to e to the j omega. Now, in general, z is a magnitude rho times e to the j omega, right? Also, the thing is, as the DTFT is to the Fourier transform, so the Z transform is to the Laplace transform. Here, the Laplace transform allowed you to build systems, right? It could implement filters. Same thing with the Z transform, and we saw that, right? With difference equations or with lumped, with delay lines and things like that. Do y'all remember that? So these are the parallels you should be seeing by now, and it should be clear. Now, when we did, well, let's see, we're down to this point. Now what I'm going to do is talk about more applications of really implementing or applying the Z transform to filters. And this is in Chapter 8. I'm not going to cover all of Chapter 8, just what I consider the important things. And please understand something. The parallels I'm showing here, you have to kind of let sink in and understand. And because these are not disjoint, everything's linked together, and you're going to see how the linkage occurs in your a lot of your upper level courses. Now, I know you had Laplace transforms when you had differential equations, but you probably didn't really appreciate just how many things you could do with Laplace transforms in terms of design, stability analysis, and all that. All right, now, what I have here today, I'm trying to just get the highlights here. So this is Chapter 8 for discrete filter representation. In general, if you have h of z, we're going to just start with the Z transform. You're going to have some constant k or c. It's a scale factor, it can be anything. And then you're going to have, we're always in terms of really numerator, polynomials in the numerator denominator. Here you're going to have z minus the first zero times z minus the second zero, call it z2. And it keeps going on. In other words, all the zeros are in the numerator, and I think everybody understands. Whenever one of these pairings is a zero, the whole function's zero. Do you follow me? Unless there's a cancellation. Everybody understand that? The poles are downstairs, so it would be z minus p1, z minus p2, and I can go on and on about this, but that's basically the way you see a Z transform written, typically. It's usually a numerator over denominator where they're both polynomials in Z. Now you can multiply them out, but that just sets the stage. So what if you wanted to talk about understanding the frequency response of this? Now I'm going to tell you, this is only for getting a general understanding of this in the real world, and you would really just use your computer to actually do this. But I'm telling you, it's important at least to have some insight, especially for the notch filter that we'll get to. So I'm going to do this, and I'm going to use the example in the book. We're going to have a system with 1, 0. This is an example. 1, 0, and 2 poles. And I'm going to show you how to interpret what's going on here from the Z-plane. Now, I'm going to just say that, so for this one, I'm going to have h of z. This is the actual transfer function. There's going to be some constant k, and it has 1, 0, so it's going to be z minus z1, and it has 2 poles, z minus p1, z minus p2. This is about as simple as it gets. And with this one, the next thing I'm going to do is write an equation here. Now, when I look at this 0, z minus z1 right here, if I want to take a look at the frequency response of this, so now I better put this down. I'm looking at the frequency response. Frequency response. You first let z become e to the j omega. When I say frequency response, that means capital omega. Remember, you're in discrete time, so it's capital omega. And we know that's really going to repeat itself every 2 pi. So between minus pi to pi is usually the extent of where you look. But there's more to this. So now, because we're in the z domain, we're in the z plane, we're going to have e to the j omega minus z1 be equal to, now what I'm doing here is this. I'm taking a look at the first 0 right here. And I'm going to say this is equated to some given length, and the book calls it L1 e to the j psi 1. And I'll get to how to interpret that. This is a 0, so, but whatever frequency you're at, right? You may not be at a point where you get an absolute 0. You subtract the 0 from there, and that's when you get some length at some angle. And I'll show you the interpretation in a second. As a matter of fact, I'll show you now. Let me draw these up individually. So now we're in the z-plane. And the first thing you do is always draw your 1 circle. Well, it's not good. It's 1 circle. Try that. So this is the real axis, and this is the imaginary axis. And now I'm going to go ahead and put a 0. Doesn't matter where I put it. I'm just going to put it, oh, wait a second. I think his thing in the book, he wanted the 0 at minus 1. So if you look at this, if this is the real axis, this is the 1 circle, and you better just put this down. This is going to be e to the j omega right here, where this would be omega, and this is called the 1 circle. Right there, because it's got a radius of 1. So my 0 is here, and the way I usually show a 0 is this. You put just a little circle there to indicate a 0. Now, if I look at the distance from here to here, just follow me on this. That distance has some magnitude L1. That's what this L1 represents. And it's got an angle of phi1. Well, this is phi1. Now I'm going to stop for a second because I know this is something kind of new. Remember, we're in the z-plane. The z-plane has an imaginary and a real axis, right? Z itself has a magnitude times e to the j omega, right? That's any value of z, correct? We're doing a frequency domain analysis, or we're looking at the frequency response of this. The frequency response always occurs when z is equal to e to the j omega. In other words, that's the frequency response. That's like a DTFT. You follow me, class? So what I'm going to do is I'm picking a point here, And I'm looking at the distance between here and here, or the length L1, and the angle. And I'm saying, when I take a look at this the first zero right here, I really have the distance difference between Z, which is e to the j omega, right, minus Z1. Well, Z1, I've arbitrarily set it minus 1. So that's the length, and this is the angle, or that's this right here. You follow me? I didn't put a value down. I don't want to. I just wanted to give you a quantitative understanding. Do you follow me on this, class? Now the next thing, you can also see one thing though. At what, when actually omega goes to what? Pi, you have an absolute zero, don't you, class? Do you follow me on that? Can you all see this, class? You can see that because this length will shrink to 0, won't it? All right, now the next thing is you're going to have poles, too, and there's 2 of them. I could put any value I want down, but the poles would be e to the j omega minus p1 and e to the j omega minus p2. Now this will have some length, and I'm going to go with his designations in the book, d1, d2, and some angle e to the j delta 1 and e to the j delta 2. I'll show you what I mean by this. This is showing.
That's why you decide.
What?
Choose Z1 arbitrary or it should be real.
I set this first 0 equal to minus 1 here. This is Z1.
So if Z1 was imaginary or a combination of imaginary,
You can put the 0 anywhere you want. Remember, you don't have to reach that 0. You understand this? When you do a frequency domain analysis, there may be technically a 0, but if you're just looking at a frequency domain, you may never get an absolute 0. Do you follow me in this class? Zeros just mean that whatever value here, Z needs to be such that this quantity will be 0. It may not be obtained in the frequency domain analysis. Do you follow me, everyone? All right. I mean, are you with me on this one? It's important. The zeros just make this function 0. They don't make the frequency domain response 0 necessarily. They make the Z, a value of Z here, right? Does not, you see, Z has a magnitude e to the j omega, right? If we're talking about a real frequency domain response, then we're talking about rho being 1 and Z just is e to the j omega, right? Now that's like the DTFT. Those are like frequencies. That omega there is equal to small omega times TS, the sampling period. So that's realizable, it's observable. All right, but in general, these zeros don't have to, I mean, when you do a frequency domain response, you don't have to get an absolute 0 for that, all right? Just like with the poles, if you had a pole here, all right, of minus, or say the pole was 2. Well, if you're doing a frequency domain analysis, the magnitude of e to the j omega is 1. You'll never have an absolute 0 there. Follow me on that? Or an absolute pole, pardon me. So you never obtain it. Anyway, next I have 2 poles, and I'm just going to put them in arbitrarily. I'm going to put one here, call it P1, and one here, call it P2. Now I want to tell you one thing about poles too. It's important to know this. Lots of times they appear in conjugate pairs. The conjugate pair means they'll both have the same magnitude, only the angle of one will be opposite the angle of the other. Do you understand that, class, when I say conjugate pairings? So that happens all the time. These look like they're getting close to conjugate pairs, but now you draw a distance from here to here and from here to here. And for P1, that distance, I called it D1. The angle is always taken from the real axis or the horizontal axis to the right of that point. Measured to the actual vector that's drawn from the pole to the point of observation of e to the j omega. Follow me on that? That's the angle they're talking about right here. And this one likewise, this angle here would be negative, but it would be 2, and this distance here would be d2. Now, what I'm really trying to do is show you that this transfer function here I have really is something where you have k, and this can be related as a distance at an angle, and this can be related as a distance at an angle, and this is a distance at an angle. Are you with me, class? Now listen carefully to the next part. So if I do this, I can write my h now, and here I'm going to look at the actual frequency domain response. So z goes to e to the j omega. So I have e to the j omega. By the way, in a lot of books, they don't put e to the j omega. It's a function of omega, right? You don't have to put e to the j omega, just h of omega. And they do. That's equal to some k. Now follow me. The first zero is this. It's L1 e to the j psi 1 over d1, right? E to the j gamma 1 times d2 e to the j gamma 2. Mark with the diagram. Does everybody understand that so far, what I've done? The thing that troubles you is this. You're saying, well, that distance, L1, is a function of the angle. You're absolutely right. I'm not arguing that. What we're going to do is get a little insight to something in a second. And this distance right here, d2, is a function of what omega is, isn't it, class? So both, it's almost like I'm putting this down here, but so what? Well, what we're saying is if we take a look at a specific value of omega, just hold everything constant, don't rotate it in omega, just hold it. Then really what I can say is this down here is equal to some k times L1 over D1, D2, and then it's times e to the j, now follow me. All these terms right here are just phase, aren't they, class? So I can take e to the j psi 1, and then I can subtract delta 1 and subtract delta 2 from it. Are you with me? I did this for a specific reason. Please listen. When I take a look at this, do you see how this whole term right here is just a magnitude? Yes. At a given omega, it says that is only a magnitude. The angle here is based on these three terms that are added together, right? Now, let's interpret this, for instance. I put the 0 right here on the axis, didn't I? That means there is a value where this function in the omega domain will have an absolute 0 because this line is going to shrink to 0. Do you follow me on that? The two poles I put off that axis, which means the function will never go to infinity. Do you follow me on that, class? No matter what omega is, it will never go to infinity. How many see this right here?
That's because there's no absolute 0 over there?
No, well, it's because if this pole was on this axis, then what happens? Then finally the distance would shrink to 0 and you would get an 1 over 0 term, right?
Yeah.
But there is no absolute 0, means the system here, and the poles have to be inside the one circle. The system has no infinite values. It doesn't have anything that's going to be an infinite value for the filter response. All right, just keep this in mind. Now, let's talk about how you would get the frequency response of this if you were thinking about it. The best way is just running a computer. But when you look at this thing right here, what do you see happening? Just think about this for a second. When is this going to be the minimum value? For what value of omega? Remember, omega is this measurement to this point. So if this little thing's rotating around, what value of omega makes it 0?
Pi.
Right. Omega equals plus or minus pi, right? That's when it goes to 0. That's at the extreme of the frequency response, at minus pi to pi. It goes to 0. Now, where does it have its maximum? Just think for a second. Think about this line right here. Where does it have its minimum value? Because when this is minimum, the function is a maximum, isn't it, class? Does this make sense to everybody? Think about this. As this distance shrinks, we're taking 1 over that distance, right? Y'all follow me?
Okay.
All right, now maybe I didn't make it extreme enough. Maybe I should have put that pole really close there. But what I'm saying is, if I made that pole here, then you could say when this distance is a minimum, or when you're right there, it would make the function a maximum. Does that make sense to everybody? And go ahead.
Yes.
Okay, I thought it was. And likewise down here, what you really do is, as you're going around here, you can see when you reach this point right here, then the distance between here and here would be a minimum, right? And you can figure out the approximate angle or the value of omega that would cause that. For this one, I was trying to make it about 120 degrees, but I didn't get there. So you could say at about 120, you're going to have a maximum, and at about minus 120. That's what I was going for. Are you with me, class? Now, this is only really a qualitative way to understand this. If you were asked to estimate how this looked, I'm just going to try to do justice to this. And I'm really going to go from 0 to pi. I know at pi I got a 0, and this is going to be magnitude of h of e to the j omega. He discusses this in his book, but he really doesn't go through the thought process. All right, you all agree it goes to a 0 here, right? What's the value when it's 0? When omega is 0? Well, you can just take one look over here, and what happens? If I have that, what do I actually have? When it's 0, I'm right here, am I not? All right, well, what do you have? Well, I have this distance, which is 2, isn't it, from here to here? So on top, I would have 2. Just try to follow this. Do you agree with me, class? This would be on top. It's a 0, right? Then I divide it by this distance and this distance, right? Now, can you sort of intuitively see that the sum of this distance times this distance here? Yes, sir.
Did you draw the second line for the distance incorrectly? Because you drew it.
It should be to this point.
Okay.
My bad. I'm just telling you, you could qualitatively get a handle on that, can't you? Again, not exact, qualitatively. Do you all see this? When I'm at 0, I basically have 2 divided by this times this. And it depends where these are. But basically, you can say, if this is 2, this might be 1.5. 1.5 times 1.5 is greater than 2. Do you give me that? So at 0, you're going to have a value that has a magnitude less than 1, but still not 0, right? And it's going to have 2 major bumps. One at this angle right here, and one at this angle. Now I try to make it at 120 degrees, or really a 2 pi over 3, or minus 2 pi over 3, but I didn't get there. What this allows you to do is this. You know you're going to come here, you're basically going to have a bump there, and if you went down here to minus 2 pi over 3, you'd have another bump here. And as you approach pi, it's going to go to 0 like this. Now that only gives you a qualitative understanding. But you can say one thing for sure. This is not a high-pass filter, just by looking at it. Because look at 0, you're passing a fair amount. Follow me on this, class? You'll get a better understanding reading this chapter. All right, I'm just giving you this discussion because he does, and he tries to, from a drawing perspective, show you what the frequency response is. That's all he's doing in the first couple of sections. He doesn't actually, he does implement a few things. Now, he talks about filters, and I'm going to put this next part down. It's kind of important. And the real way to do this, by the way, is to always plot it. All right, you're never going to really be somebody that can pick out a fifth-order filter's response just by looking at it, unless you work with that filter over and over again. So the next thing to do is talk about implementing filters, a few other things too. This gets interesting because, you know, if I'm sitting where you are, and I got a curiosity about this, I want to see this stuff implemented. I want to see how I'm going to use this to actually help, maybe, I don't know, do some sort of digital signal processing on an album I recorded or something like that. I'm always thinking, when I was in your seats, it was always building stereo equipment, hi-fi equipment. How does that help? Why are you telling me this? And it does make a difference when you've got that natural curiosity about how does it affect me. All right, so now, all right, got a bunch of stuff to tell you. First, let me do this. All the filters with Z-transforms that we're talking about are called, he's going to call auto-regressive moving average. This means auto-regressive moving average filters. Now, I'll explain. Auto-regressive. They're automatically going back and looking at past values. They're regressing. And they're doing something with past values to predict future values. Do you follow me on this? Now, this is something that microcontrollers and microprocessors are great at. Storing data with a real clock cycle, and then using that data in real time and doing something with it and predicting, and giving an output. You follow me on this? You all know how a microcontroller works, or at least you have an idea, right? Was it Arduino? Is that what you guys use these days? And you use what have you ever programmed microprocessors at all? All right, well, in all cases, you can do these calculations seamlessly in real time, very fast. So that's what you're going to see this all the time. An autoregressive moving average filter. It just means it uses the values of the past to predict the future, and in some way it's a filter. All right? You're not saying what type of filter it is. So I'm going to tell you there's low pass in the book, there's high pass, there's band pass, and there's band stop. There's a bunch of them, and they're well defined. And I can go through each one. I can tell you one other thing though. Does anybody remember how I told you if you had a filter design in the S domain, in H of S, high pass, low pass, or band stop, you could simply use a bilinear transform to get the value of Z, replace S with Z. Does anybody remember this?
No.
Yeah, you do. Sure you do. Do you remember this? Where you could take that filter and literally replace the S value with a modified Z value, and now you would have the Z filter, Z transform filter, that would do the same thing. Let me just mention this to you, because this is something that's important. If you got your books, just look it up. It's called a bilateral transform. It should be, or bilinear transform, pardon me. Remember how you had, for the Laplace, it was x of s is equal, this is the real reason I don't spend time with low pass, high pass, band stop, but I'm going to spend my time on notch, because this is something a little different. X of s is equal to the integral from 0 to infinity of x of t, right, e to the minus st dt. That's the Laplace transform, right? Now, I said if you had this, and you made x of t, sample of t, equal to delta of t times not delta of t, x of t, right, times delta of t minus nts here, n goes from 0 to infinity, that would be the sample value. Do you remember this, class? How many do? We did this several times. We did it for Fourier as well as Laplace, right? Now, what happens next when I do this? If I take this and stick it in here, well, actually I can say that this is equal to what? The summation here of x of nts times delta of t minus nts, right? N equals 0 to infinity. I'm just modifying this x sample of t, and that's just what? Taking the values of x of t and sampling them at what? An interval of ts, right? You follow me on this? This is the bed and nails function, right? The cone filter. How many remember the cone filter, right? All those impulses, right? Now, when we take that and stick it in here, what do we actually get? Well, we get the integral from 0 to infinity of x of st. So it's going to be this, summation from n equals 0 to infinity of x of nts times delta of t minus nts, right? It's that times e to the minus st dt. I've just replaced x of t with the sample values, right? It's still a Laplace transform. Do you all agree with me here? This will ring bells. You'll remember what we did. Now we came to this point, and I made the argument. Well, this x of nts, the reason I did it is because the only value that's of importance of x of t is with t equals nts. Do you agree with that? Because the delta function is on only at that instant, right? So I put it in there. But now when I look at this right here, and I should have I do have the summation there. I can interchange the integration with summation. I'll do that one last time. So now I'm going to put the summation outside. N equals 0 to infinity. And I'll put x of nts here. And now I have the integral from 0 to infinity of delta of t minus nts times e to the minus st dt, right? Remember, and I've still got my summation, but what is this value here? Well, still have x of n ts right here, but what happens when you integrate a delta function? You find the value of the functions adjacent to it that are at the point the delta function goes to infinity. Do you all agree with me, class? What are those values? NTS, right? For all values of n. Do you all agree with me? So you simply put e to the minus s times n ts. Now, this, believe it or not, is the z transform. Because this is really, if we suppress ts, we get a summation here, n equals 0 to infinity of x of n, right? And then we have e to the minus n sts, right? And we notice that the z transform, if it was a z transform, x of z would be the same form of the summation, n equals 0 to infinity. And then you would have x of n times z to the minus n. Do you all follow me here? This is how we get the z transform. We developed it out of Laplace. Do you all remember this now? How many do now? At least me doing it. If you don't remember exactly, you'll understand the reason I'm doing it is because you know all those filters back in your day of circuits, right? You know what a low pass, high pass, band stop are, and therefore you know h of s for them. That's where I'm going with this. So I'm not going to spend a lot of time on those filters. And here's the trick. Follow me now. Now, do you all see how these two terms have to be equated? So I have to have z to the minus n equal to e to the minus n times sts, right? And ts is just the sampling interval. Y'all remember this? I'm trying to link all this stuff together. I know how it can become a blur.
What does that say, e to what?
This is it's just the argument here. E to the n sts, or e to the n sts, right? N is an integer, s is s, right? Real and imaginary values, and ts is the sampling interval, right? Now, if you take the log of both sides, right? I mean, do you all see how n can go away here, right? Does everybody give me that? N's on both sides. You see how the minus sign can go away, right? You with me on that? Now I have that. Now what do you have? The log of z is equal to what? STS, or the log of z over TS is equal to S, right? Y'all agree with that? Now, remember, you have functions that are h of s for low pass, high pass, band stop, right? You all remember that? You've got them. If I want a low pass filter and I want it with z now, not s, I can do that. But there's one trick here. How many remember the trick with natural log of z? Anyone? What's the natural log of z? What was it again? Do you remember? Say it again. Say it. The magnitude plus
J times the
Oh, you're doing complex variables. I'm talking about the simple relationship where we did an expansion of the logarithm of z. Do you remember this, anyone?
We're redoing it. We got no.
There was what? For this one, what? There's going to be what? It's actually z minus 1, isn't it, over z plus 2, I believe? But I actually got to check that myself because I don't use this one. Well, I'll look it up for myself. I wasn't intending to go here. It's the bilinear transform. 504, there's one page I suppose it has it. It's actually he does it in S. He's going to say this is equal to 2 over TS And then it's gonna be times z minus 1 over z plus 1. All right, this is the deal here. This is called a bilinear transform. Right here. And that means if you have any function, let me just spend 1 second on this because it's important. And I know how easy it is to not see the linkage here. Let me just do this for you. Y'all understand if we want low pass, high pass, band stop filters, you have information to get those. Back in the day, you can get 20 dB per decade roll off, 40 dB, all that. You've done that with your linear, really your circuits courses. If you wanted a low pass filter, a simple low pass, you could say it's K over S minus or S plus really A, right? And A would be the frequency, the low pass cutoff frequency, right? Do you all agree that's a low pass filter right there? Give me a show of hands, how many do? How many don't?
I mean, it's not that I don't agree.
Well, normally how do you actually do this? You'd say H of S go to J omega here would be equal to K over what? A plus J omega, right? And then if you wanted the magnitude of that, magnitude of H of J omega here, that's equal to K over the square root of A squared plus omega squared. Do you agree with me there?
Yeah.
All right, how many do right here? You understand what I've done there? This is as simple as it gets low pass filter. Now what does that look like? If I plotted just magnitude of H omega here versus omega, you would have this, right? And this point would be what? That would be A, would be called the 3 dB point. How many remember that from your labs, right? You had to do this for your laboratories. Yeah, I mean, how many did this in your laboratories? You don't remember doing that? This is a filter response. You did it in your labs, right?
Did it, but it wasn't.
They handhold you through it. They give you the circuit.
They give you
run a
everything.
LabVIEW script and it spits it out and you put it on your lab report. We don't really learn anything in labs.
That's right.
All right, well, I appreciate your honesty. I'm trying to make this clear to you. What they're trying to show you, they're trying to make you see that this is a Laplace transform. You see this as a simple pole, right? One pole there, right? Now if we sweep frequency, what do we get? We put S is J omega, and we take the magnitude. That means this, well, if you look at omega equals 0, you get K over A is the value right here, right? Now sweep it out. When all of a sudden does omega become important? When it's the same proportional value as A, right? And then at that point, all of a sudden the 1 over omega takes over and starts breaking downwards, doesn't it? At 20 dB per decade. I'll spend more time on that later. But what you see is, you've got this. You want a low pass filter in Z? Take that equation and just replace S with this, and now you have a low pass filter in Z. I don't need to go through all the hand holding and when it's low pass, high pass, band stop, band pass stuff in chapter 8. You've got that. Do you understand me, class? As a matter of fact, you know exactly what the break frequency is. It's omega or 2 pi f equals A right here, right? So you have that information. I'm going to help you through the notch filter and you'll see how all this overlaps. I'm trying to jog your memory so you see how this all links together. I really am. So getting back, I didn't mean to take off on this one, but now getting back to a filter that's important. It's called a notch filter. And this is one that's important. Now here's the real reason a notch filter is so important to you and me. Have you all ever had the opportunity to listen to something and there's an irritating hum or buzz? Something just drives you nuts and you'd love to get rid of it.
Yeah.
The way you get rid of it usually is with a notch filter. That or you unplug whatever the thing is that's making it. But it used to be hair dryers back in the old day. I don't know what causes that stuff nowadays, but there's normally, if there's a single frequency, usually there's an oscillator somewhere that's just interfering. And I teach EMC and I'll tell you that's one of the biggest problems they have is two systems interfering, especially in electronically dense environments like aircraft carrier decks and stuff. They're always trying to stop that one from interfering with this one. So the way we do it is with, and this is in the digital domain. Now this doesn't have a good analog, well maybe it does, but it's not easy to see, an analog parallel that you can pull from. So for notch filters, let me first tell you the way it works. with notch filters, you want to get rid of something. The thing you want to get rid of we want to get rid of something that has a frequency omega I. So we want to get rid of this. I'm going to put it in my vernacular. We want to get rid of that. It's bad. So that means what I look like, I actually have some x of t, I'm going to go continuous time, some magnitude a times cosine of 2 pi fi here times t plus phi. Now this is a simple cosine waveform. Note this, the 2 pi fi is really omega I. So I can write this as x of t is equal to a times cosine of omega I t plus phi. So this would be in continuous time. You're familiar with that, right? And if it was 60 hertz, then f here would be 60 hertz, and omega I would be 120 pi radians per second. Follow me on that? 60 hertz is a very irritating frequency, you'll find out. You'll hear that buzz bother you more than any other buzz early on in your life, and for the next, say, 10 years. And then there'll be the 400 hertz frequency will be an irritating one if you get in the aircraft industry and stuff like this. But you'll see there are certain frequencies that are really irritating, that I found out. Now we're going to take a look at what happens when we actually have sampling that has this irritating frequency. When we sample that, now we have S sampled, right, of t is going to be a times cosine of some omega I times n times ts plus some phase angle. And here, what we really see is we have an x of n. Please write this down. This one I'm not going to go over again. And what I have here is omega I times n plus phi. And I notice that my omega I is actually small omega I times ts, where ts is the sampling interval. Does everybody see this, class? All right, now please listen. Try to make this as real as I can. This is the guy that's irritating me. When I go through and sample it, this is what it looks like. Now I'm getting into my capital omega domain, right? Now I take a look at this, and I want to design a filter that gets rid of that. So I want 2 zeros at that frequency. All right? They're going to be conjugate pairs of each, the conjugate pair, because I want to get rid of it. So I'm going to have 2 zeros, they're going to appear, and they're going to knock it out. So I'm going to have this. This is my h of z. And I'm just going to call it h of z right now. So I'm going to say that's going to be 2 appear there. I have z minus the first one, which is e to the j, or minus j omega I, right? Times z plus e to the j omega I. Now, you'll notice what I've done there. I've got conjugate pairs for the zeros, right? But whenever omega is either plus or minus that value, it's gone. There's a 0 there. Do you follow me? Now, I'm also going to put poles in here, and I got to tell you one thing. Any of these things, if you got zeros, you're going to have poles. You have to do this with a z transform. There's no way around it. I don't have enough time today to talk about it. But I'm going to have 2 poles, and it'll be at z minus a times e to the j omega I, and z, sorry. Did I have that right? This should be a minus. And then z minus a e to the minus j omega I. Now, listen. Here's what I'm doing here. This is the simplest possible thing. I've got a 0 right at that frequency. What I'm doing is putting a pole at that frequency with something that's softening its value, A. Now I'm going to adjust A to give me some width to this notch filter. I'm not going to have enough time today, but when I multiply those things out, next time I'll pick it up there, what you're going to see is we're going to get a filter in time, an auto-regressive moving average filter that will easily get rid of that annoying buzz. And it'll do it with an extreme, in a way that doesn't affect the other stuff very much. All right, I'll pick it up there, but I'm trying to make this as practical as